Welcome back. So our next example is going to involve a hypothesis test for a proportion. And the new tool that we're going to use is we're going to use the standard error together with the normal distribution in order to figure out how to resolve this hypothesis test. But we're going to do this for a proportion now instead of a mean, which is on some level exactly the same as the previous example, but it does have some differences in some of the calculations. So in order to make it definite, let's talk about a proportion that might be an unemployment rate. So suppose you have a vulnerable population and you're trying to assess how high the unemployment rate is. And suppose for some reason there's this 10% cutoff that you're particularly worried, is the employment rate greater than 10%? Okay? So if that's your hypothesis, the unemployment rate is greater than 10%, then you would have an alternative hypothesis that would look like this. More than 10% of the population is unemployed. So P is going to be greater than, notice, 0.1 because that's the same as 10%. And then the null hypothesis will say exactly 10% of the population is unemployed. And so it will assert that P is equal to 0.1 exactly. Now, of course, we have to assume here that this is a data-driven investigation. And so let's assume that we collect some data. And so let me describe the data set for us. So we collect some data. Now, anytime you collect some data, then you have to have a sample size. So let's assume that our sample size is really pretty good. I'm going to take a sample size of 1,400. So I'm going to assume that in this population, we, in some responsible way, contact randomly 1,400 people, and then we figure out whether they're employed or not. By the way, with something like employment statistics, it's much easier to actually use government data and use records that, because all of these things are in databases. But let's just assume that we just do a simple random sample from the population. So, so N is going to be, for our purposes, 1,400. And now, having done that, then we will measure some proportion within that population. And let's say the proportion is equal to 11.6%. Or really, that's going to be P equals 0.116, okay, compared to this. It looks a little bit bigger, but it's not quite clear whether it's definitive. Now, notice here I've called this P, but that's not actually P. That's the proportion within our sample, which is the sample proportion, so that's P hat. So it's actually P hat, which is measured to be 0.116. Now, there is some natural variability that we should expect. And so let's talk about the standard error. So, so what we want to do is we want to take this as our data, and then we want to resolve this hypothesis test. But the standard error is going to be very useful for resolving the hypothesis test. Now this is a proportion, and the standard error for a proportion follows a completely different formula from the standard error for a mean. So we're going to use that formula instead. The formula that we need is P times 1 minus P over N and square root of the whole thing. So this is going to be 0.1 times 0.9 over N, and that's going to be the square root. Now, you might say, why am I using 0.1? Why not use 0.11? Why am I using 1 minus 0.1? Why not 1 minus this? Well, the standard error is a technique that we use to describe the variability that we would get, that would come naturally as a consequence of sampling if the null hypothesis was true, right? Even if the null hypothesis were true and exactly 10% of the people were unemployed, we would still see natural variability. And this hypothesis test is ultimately trying to measure, do we really believe that this could result from the natural variability if the null hypothesis were true? And so, if possible, we should calculate the standard error under the presumption that the null hypothesis is true because it's part of the null story. So let's write down the null story here. So what is the null story? The null story is, first of all, exactly 10% are unemployed. And P hat, so any measure of 1,400 from a population would show some variability. So P hat is naturally variable. That is, anybody who goes out and randomly samples should anticipate some variability even in the result of that study. So it's naturally variable, but we can describe the variability exactly. It should be a normal distribution. How should it be centered? Of course, it should be centered at the exactly right value, which under the null story is 0.1. So 0.1 is the value we should have gotten for p hat. It's the most likely outcome. It's what you would expect. 0.1 should be the anticipated value. But, so I didn't finish this calculation here, but it is naturally subject to some standard error. And if we work this out, I worked it out before, this is 0.008, which is a pretty small standard error. And that's really great. Like we really hope for small values of the standard error. Why is it so small? Because the sample size is big, right? A large sample measures things precisely. To measure something precisely is to measure it without much error. And so this is a reflection of the fact that the sample size is so nice. So here, this standard error is the normal variability of p hat. And so basically what we're saying here is p hat, the measure that we performed, should have been naturally, normally distributed with a bell curve, and it should have had the center of its distribution 0.1. That's the right answer we should have gotten. And it should have had a natural variability really quite small, 0.008. Now, what we saw was it was a bit larger than 0.1. That still is possible under the null story. So so p hat measured was randomly off by how far? Well, this much minus that. So it was off by 0.116 minus 0.1, which is 0.016. And the z-score is 0.116 minus 0.1 divided by 0.008. The key thing about the z-score is it's measuring how far off from anticipated our results are in units of standard errors. And this thing, because to be honest, I kind of rigged the numbers, this thing is exactly equal to 2. So we get a z-score exactly equal to 2. You can see here when you subtract this, you get 0.016, and then you divide by 0.008, and you get 2 exactly. And what that means, what does that mean? So under the null story, what that means is, well, oops, you just got 2 standard errors away from the normal result you should have gotten. And you got that for no good reason other than just the randomness of sampling. So, you know, stuff happens, right? You just ended up a couple standard errors away from the anticipated value. And now we get to the key question of the p-value. Like, what are the chances of that? What are the chances of getting 2 or more standard errors off from where you expect it to be? And this is where the normal distribution really comes in and saves the day. If we have a normal distribution, and I've plotted a normal, this is my by hand normal distribution here. If you have a normal distribution and you know how to use it, you can go to here and you can ask yourself, how much area is there? Because the total area is the total possibility, it's the total everything that could have happened. The total area on this graph is all the random stuff that could have happened in the null story. And basically, this is what did happen. We got 2 or more. So we got 2 actually. So what we're really asking here is, what are the chances of that? What are the chances of getting 2 or more just randomly and accidentally? And then the normal distribution will come in, save the day, and answer our question. So again, there's a little bit of a fiddling with an online tool so that we can get this result here. But what it amounts to is we have to measure the area of this tail. This is called a right tail because it's a, because it's, this thing is called a tail because of its shape, and then it's on the right-hand side. So this is the right tail, and basically we just need to know how big it is. And that will give us the p-value. So the size of this right tail is, well, it's going to be about 2.5%. So it's about 2.2%. So this is going to be 0.022, which is actually our p-value. So the p-value here is 2.2%. Actually, I think I'm rounding that the wrong direction. Let me be careful here. 2.27. So 2.27%. So the p-value is 2.27%. And basically what that's meaning, what that means for us is it's really not at all probable that you would get 2 standard deviations away from the mean or more. 2 standard deviations from the mean is actually kind of a big deal. And a z-score of 2 is actually kind of a big deal. That means that that's actually not very probable to happen by chance. So the story of the null hypothesis describes an event which has a z-score of 2. And it's not probable to get 2 standard deviations away from the anticipated value. It's actually quite improbable. The chance of that is 2.27%. And that's underneath our normal threshold for statistical significance of 5%. And so the p-value is underneath the alpha value. And so we do what we usually hope to do in a statistical study. We reject the null hypothesis, and we say the alternative hypothesis is true. So this is the usual outcome that we're striving for if we're doing a statistical study. Unfortunately, the alternative hypothesis is bad news in this case, but that's just sort of on a moral level, it's bad news. Scientifically, we succeeded, in a sense, at proving the point that we were trying to show. So, here, the outcome of the thing is decided by the p-value, which comes from the null hypothesis. Everything that happens here is exactly what happened before. Everything that happens here is exactly what happened when we did confidence intervals. The only real difference is that we're cleverly calculating the z-score and then cleverly comparing it to this base foundational distribution, which is the normal distribution, in order to get the p-value. Now, you probably can't look at this picture and say, oh yeah, it looks like 2.27%, and that's a little wrinkle that I've left out of the lecture, and I'm going to show how we can use some online tools to get the exactly right answer there. But once we get that, then we reject the null hypothesis, and off we go. So that's how we perform a hypothesis test for a proportion using a z-score and comparing to the normal distribution. So there is a wide variety. We've done this for a mean, we've done this for a proportion. We can do two-sided, we can do one-sided, we can do comparing one sample versus 2 samples, and there's a wide variety of these examples. But there is also a basic overarching principle here that guides all of them. You don't need to master like every single scenario in order to know what's up here. You just have to understand the basic guiding principle. The guiding principle is there is always a story, what I'm calling the null story. There is always a story about what happened. And that story predicts that some measurement should exhibit some amount of variability. And then there is always an actual measured value. If you have the story that says it should have been this, and it should have varied by such and such, no matter what it is, whether it's a mean or a proportion or a difference of 2 proportions or a difference of 2 means or whatever, no matter what it is, if you have a measured value of the thing, and then you also have an anticipated value of the thing, and you also have a standard error so that you can relate how much variability you expected. As long as you have that information, you can ask yourself, how many standard errors away from the anticipated value am I? And that answer is the z-score. And then with the z-score, you can quickly refer to no matter what else is going on, whether it's proportions, means, whatever, with the z-score, we can quickly refer to the normal distribution, and we can resolve the hypothesis test. So the overarching principle here is there's always a measured value, and there's always an anticipated expectation for that value that comes from the null story. And there is also always a standard error that guides your expectation of the variability of that thing. If you know those 3 things, then you can calculate a z-score and you can resolve these tests.